Hello everyone, welcome to today's lecture on quantum computing in which we'll discuss irreversible and reversible classical and quantum gates. Let's start with the definition of what a gate is. A classical gate defines a function f from some input bits, a string of inputs of length n, to some output bits, again a string of zeros and ones of length n. And you can say if this function is a bijection, then the circuit is reversible. A bijection, just remember, means that for each input, there is only one definite single unique output. It means you can always conclude back from the output to the input. So if the output, if you're given the output of a reversible function, then you can uniquely construct this input. And a gate which is not reversible is called irreversible. So that doesn't come as a surprise. So for reversible gates, we require that the number of n input bits is equal to the number of m output bits. And why we consider reversible gates is one of the most interesting things. So one of the original motivation comes from Landauer's principle. I don't know if you heard about that before, but maybe we briefly talk about Landauer's principle before we continue. So let's assume you examine a single bit in your computer. And this bit is 1 degree of freedom with 2 possible states. And now the rest of the computer has lots of other degrees of freedom and can be in one of many states. And one of the fundamental theorems of physics says that phase space cannot be compressed. So if we apply this principle to the process of erasing this one bit that we just talked about, then let's suppose there is a physical process which irreversibly erases a bit. So it doesn't matter if the initial state is 1 or 0, it always goes to 0. Now, since phase space cannot be compressed, if we perform this irreversible operation, then phase space must bulge, so to say, must bulge out along the other degrees of freedom, so along the other bits. In particular, this means that the entropy of those other degrees of freedom must somehow increase. If we now work through how much it must increase or by how much it must increase, we'll find that this is approximately Kb, which is the Boltzmann constant, times the temperature, the absolute temperature. Well, let's write that down. So if you've seen that before, the Boltzmann constant, which relates the average kinetic energy of particles in a gas to temperature, times the temperature to logarithm base 2. So logarithm base 2, I give you an example for that too, is one example would be the logarithm of 16, which is 4 because 2 to the power of 4 equals 16. So if we now try to work out how much the entropy must increase, we remember it increases by that factor for a system in thermodynamic equilibrium, which is then called Landauer's erasure principle. So erasing a single bit of information necessarily results in the increase in entropy of the other degrees of freedom by a value of that. So this principle itself, it motivates us to consider reversible computation. So and for today's modern computers, we're not near Landauer's principle at all, or Landauer's limit at all. They dissipate something like 500 times as much heat as Landauer's limit, but certainly there are exceptions that this will change as we build smaller and smaller computers. So it's getting better over time. Now, one thing we want to worry about is whether the power of reversible computation is the same as the power of irreversible computation. And some results which basically say that there are some results which basically say that they have the same computational power. But it's nice to see at this point. And a trick we can use to compute the irreversible functions using reversible circuits is as follows. So suppose we have an irreversible gate f from n bits to m bits. Then we can design a reversible gate which computes the same function. We just keep the input around. In particular, we can construct a reversible gate with m plus n bits, which acts like, let me write that down. Maybe let's erase some stuff here. So in principle, we can take our inputs, x, y, and create an operation that takes our input, x. Here we have the addition modulo 2 plus f of x, right? Where, addition modulo 2, you remember that's the XOR. That's another word for it. So it's easy to see that this is reversible. If we apply it twice, let's again take our original input. If we use our function that we just specified, x, and apply that twice, the result is going to be modulo 2 f of x So this was our input first. Applying that thing twice here will give us our original result back. So a function is its own reverse defined over all possible inputs, okay? Further, if we apply this reversible circuit element to x0, we have computed f of x. So let's say we apply it to x0 here as the inputs, and we obtain x f of x. We have computed f of x. Yeah, so you'll see the result of the function in that second bit here. So we can always turn an irreversible gate into a reversible gate at the expense of having a larger gate. And you talk about garbage or auxiliary bits that aren't necessarily used in an irreversible circuit, but we want to use them in a reversible circuit, which are these bits here. So we keep the input as is, we don't modify the input, and compute the output on another bit. And so if you think about an irreversible operation classically, the erase operation again, if you apply that to the input directly, then there is no way of concluding back what this original input was. And if we now get to quantum circuits for these reversible gates, we'll see that these garbage bits can have bad effects on our quantum algorithms. So if we want to simulate the action of a reversible circuit from n bits to m output bits, we want to think about options to get rid of these garbage bits. And there is one beautiful trick that Charles Bennett came up with in 1973, I think. And so suppose we have a function that takes the n bits as an input and is implemented using the above construction with which produces garbage bits. So then if I write that down, let me quickly erase that here. We want to look a little closer into the circuit notation here. We'll learn more about that later. But let's implement a very simple circuit. Our simple circuit comes with n input bits, x. Our circuit also comes with k garbage bits, which we initialize to 0. And our circuit has m output bits, which we also initialize to 0. When we talk about circuits, remember I briefly started talking about these in the second or third lecture. We talk about the evolution of our input register, and the time goes from the left to the right. And here we apply some transformation. In that case, it's the function f. Since we are talking about a reversible computation, as just mentioned before, we will not touch our input bits. Our input bits will still be n input bits, so it's the same number of bits, and in the state x, okay? Our garbage bits, of course, it's also still k bits, But then this may be, since we use it for computation, this may be in a state of g of x, since it may have used x as an input. And we have our m output bits, which are still m output bits, but these are now the function that we actually want to compute in a state f of x. Now, the trick to get rid of the garbage bit is as follows. So since f is made up of a reversible circuit, we can implement f minus 1 by simply reversing the order of all the circuit elements and then implementing the inverse of each of these elements. So moreover, we remember talked about the controlled NOT operation. So remember when we had a quantum state that, so that quantum state, for example, and you apply the controlled NOT operation to that, then it checks for the first bit and flips the second bit if the first bit is 1. So in that case, the result would be 1, 1. The controlled NOT operation is a reversible gate. So if you apply it twice, you will end up with the state 1, 0 here again, and can be used on a 0 target to copy the value of a bit to the target bit. Yeah. Look at this again. So if that state is 1, it will copy the state to the target. If you start Z0 in the original, in the configuration of, or on a state 0, 1 here, 0, 0, for example, then you could also say application of C0 copies the value to the target because that will remain 0, 0. Okay? That's why you can say controlled NOT copies the bit. So using these two facts, we can implement a new circuit. And let's do that again. This new circuit also starts with n input bits x. It also starts with k garbage bits initialized to 0. It also starts with m output bits, which we also initialize to 0. But then on top, it has another n bits, which we also initialize to 0. So you see, we have one more register here. And again, we evolve from the left to the right. That's just how time goes. We just take that circuit here, it's the same, and apply that to our registers as we did before. But now there is a difference. So we evolve this line further here. And then here we apply the controlled NOT operation. So remember, I think I showed you in one of the last lectures, this is the sign for the controlled NOT operation. And then evolve this further. Here, we revert everything we just did. So we just apply inverse f to the power of minus 1. And what we get here is our n x bits. Again, we have our k garbage bits, which we initialize to 0. Since we do the reverse here, the result will be 0. And we have our m output bits, which will be 0 since we reversed it here. But the actual output, the size m, f of x, you can find here. So the controlled NOT is really the m bitwise controlled NOT. So since we have more bits here, and it's always possible to erase all of the garbage bits. And so now we got rid of the garbage tricks, and this trick will be used all the time, often implicitly. Why are reversible gates important in general? Because there are a couple of algorithms in quantum computing that require to have reversible gates. But so it becomes more clear with one problem that we will look at the beginning. It's called Deutsch's algorithm, which in which we can turn these gates into quantum gates, which enact the reversible computation on the computational basis. Now, why are reversible gates important? There are a couple of reasons, but it will become most obvious when we look at Deutsch's algorithm. So it's one of the first quantum algorithms we will go through to show you or to discuss why a quantum computer is more powerful than a classical computer in certain cases. So as we will see in Deutsch's algorithm, we can turn these gates into quantum gates, which enact a reversible computation on a computational basis. So in particular, let's see, let's take a function h here that acts on a string of bits, zeros and ones of length n, and it produces another sequence of bits with zeros and ones of length n. And if it's a reversible gate, then we can implement it quantumly. And quantumly, in that case, means we can just take the sum here. So x is an element. X, our input value, is also an element of a sequence of zeros and ones of length n. And here we compute h of x. And here we have our original x. So remember when we talked about how to construct quantum gates in the beginning, we said we always start with the initial state and where I want to get. And this is what I want to get. So I want to compute the function h of x here. So since h of x is reversible, it will be a unitary gate on n qubits. And on a computational basis, it will compute the reversible function of h, so to say. And using the garbage trick, we can implement a general irreversible classical circuit by changing the irreversible circuit elements to the quantum reversible circuit elements, and then use the garbage trick to enact a quantum circuit, which in turn enacts the unitary evolution that we're after. And let's write that down quickly. If we have, again, our input bits here, so which is in that case 2 to the power of n minus 1, since we start at 0 here. I have the output bits, which is 2 to the power of m minus 1. Again, since we start with 0 here, then I take my input here, execute a unitary transformation here, then just what we learned before, execute a tensor product here, and just what we learned before, we will compute the modulo 2 operation with f of x and my y here. Okay, and that is important to keep in mind. So how you construct these gates, and what we've just discussed, that we can turn irreversible gates into reversible gates, and these reversible gates again, so in turn into quantum gates, along with the fact that at the cost of a factor of 2, we can get rid of all the garbage bits that we had in our circuit before. One further interesting question to discuss here is, and it's useful, is to know something about universal sets of gates for classical computing. Now, just as we discussed the sets of gates which can be used to compute any unitary operation on our quantum data, so our quantum circuit, we can also talk about gates which can be used to implement any reversible or irreversible circuit. You remember, I'm sure you've heard about the NOT AND gate, the NAND gate, short, which for each input produces, each two inputs produces 1, except for 1, 1, where it produces 0. So for 0, 0, it produces 1. For 1, 0, it produces 1. For 0, 1, it produces 1. And for 1, 1, it produces 0. And an interesting question is whether there are any classical reversible gates with 2 bits, input and output, which are universal. And the answer, in short, is no. So the smallest gate, which is universal for reversible classical circuits, requires at least 3 bits, input and output. And we can have a closer look at that. So let's take an example and try to or prove that the controlled NOT operation that we have talked about so much by itself can never be used for universal classical computation. For inputs x, y, our controlled NOT operation computes, let's say x, y, which is x addition modulo 2 y, or x XOR y. So let's assume we have n input bits given by x0 to xn, and the controlled NOT has control over the ith bit, so it checks the value of the ith bit, and it targets the jth bit. That can be represented by an n by n matrix. I'm saying an n by n matrix because you have n bits. And this n by n matrix has ones along its diagonals and zeros everywhere else, except on the ith and jth column, which have a 1. And then what we can check is if we represent the input to the controlled NOT by a vector. Now let's again take our inputs here. If we represent or supply our input to that matrix and apply that matrix to that input, then the multiplication of this matrix working with addition modulo 2 is the same as enacting a controlled NOT. Yeah? So what we see is by multiplying a representation of the controlled NOT together and doing our addition modulo 2, we can represent the action of any series of controlled NOTs on these n bits by an n by n matrix. So that's not news. We talked about that before. So you have always the same dimensionality of a transformation than you have as you have in the vector. Now, what this means is that there are at least 2 to the power of n such matrices which can be realized by controlled NOTs. Actually, there are less because not all matrices correspond to a controlled NOT. For example, the all zeros matrix doesn't really correspond to a controlled NOT. But now think about what would be needed for a universal reversible circuit. If we look at the set of reversible circuits on n bits input, then the set corresponds exactly to the set of 2 to the power of n, is 2 to the power of n permutation matrices. So, and there are 2 to the power of n factorial such functions. So therefore, we can see that there is certainly no way that a controlled NOT can be used on n qubits to reproduce all of these permutations. We can also see that even if we encode the space of the controlled NOT reachable operations, it will never grow fast enough to keep up with the space of reversible circuits. And that in turn means that the controlled NOTs can never be used as a universal gate for reversible classical circuits. And that's basically it. So what sorts of gates are universal for classical computation? It may make sense to look at that too, because just before we learned it's at least 3 bits that we need. So 2 of the most famous ones are the Toffoli gate and the Fredkin gate. The Toffoli gate is a controlled NOT, which enacts the transformation. So I will only write down, so because since we have 3 bits, it says 2 to the power of 3, we have 8 different outputs. I will only write down the ones where it changes, so where it changes the bit. So for example, if you have 1, 0, 0, that will remain the same. So it will take the first 2 ones, and if the first 2 ones are 1, then it will set the third one to 1, 2, or to 0, depending on whatever that state is. So if it means for that one, it will remain the same. But if we have 1, 1, 0, it will create 1, 1, 1. And if we have 1, 1, 1, it will make 1, 1, 0 out of that. And then we have the Fredkin gate, which is also called the controlled swap gate. Controlled swap just means, for swap, the swap operation requires 2 bits. And controlled means, so again, the first one will be the control bit. And let's say I have that input here, and the output will be, so 101 becomes 110 because it swaps these two, since the first one, the control bit, is 1. Okay, so you may try that for the different other inputs, but that's basically the functionality. So both the Toffoli and the Fredkin gates are universal for classical reversible computation, given the ability to use extra scratch bits in n fixed states. So interesting further property of the Fredkin gate is that it's conservative, so which means it never changes the number of zeros and ones in a string, because it just flips. So here, if you look at that one as an example, you still have 2 ones in the output, and you had 2 ones in the input. One reason to consider this gate is motivated by physics. So suppose that the 0 and the 1 bit are represented by configuration with different angles, or energies, sorry. Then with a logic gate, like the Fredkin gate, it's possible to conserve the energy of these bits from input to output. And with a gate like the Toffoli gate, this would be not possible. So it wouldn't be possible if the bits have different energies. It's interesting to go through these, the current physical implementation of bits, and to note whether the bits in these devices are implemented in configurations with different energies. That's that for classical, reversible, and irreversible, for classical bits. So now we want to have a look on quantum bits and see what the difference is here. So the only non-trivial reversible operation on a classical bit is X, right? So which is the NOT operation. Reversible operations on the quantum computers can perform on a single qubit, are represented by the action on that state of the qubit of any linear transformation that makes unit vectors to unit vectors. And such transformations, usually we denote them with U. So if we don't have any specific description, so we just call it U. Any such transformations are called unitary and satisfy this condition. If you remember that one, it just means the original transformation times its complex conjugate transpose results in identity. Also, the complex conjugate transpose times the original transformation must result in identity. So any unitary transformation has a unitary inverse such that its actions are reversible. In mathematics, generally a unitary transformation is a transformation that preserves the inner product. And the inner product of two vectors before transformation is equal to the inner product after the transformation. Unitary transformation is also an isomorphism between two Hilbert spaces. So in other words, what that means is, that sounds always very formidable, but in other words, that means a unitary transformation is a bijective function, a bijection that executed on one Hilbert space results in bijection into another Hilbert space. So H1 and H2 are Hilbert spaces. Basically, there's not much more to say about that. Most general reversible n classical bit operations on a classical computer. So the most general one is a permutation of 2 to the power of n factor different classical basis states, which is this one that we just saw before. The most general reversible operation on an n-qubit operation on a quantum computer is represented by the action on their state of any linear transformation that takes unit vectors into unit vectors. So for example, a 2 to the power of n dimensional unitary transformation U satisfying these conditions here, these ones here. Any reversible operation on classical bits can be associated with a unitary operation on n qubits, and U on a classical basis states of the qubit is to be identical to the operation P. So if P is a permutation of the 2 to the power of n C-bit states on the corresponding classical states of the C-bit. So since all classical basis, since the classical basis is is a basis. So basis means the basis vectors that we operate on. So remember the Euclidean space we discussed at the very beginning, where we had 1, 0, 0, 0, 1, 0, 0, 0, 1 as the basis vectors. So U can be extended arbitrarily to n qubit states by requiring it to be linear. Since any action of U, or the action of U on the classical basis states, is to permute them, its effect on any superposition of such states is to permute the amplitudes. So if you remember, in quantum computing, we're manipulating the amplitudes. And so if we write that down, let's call the amplitudes alpha n. So here we have an n bit state, an n qubit state in that case. And the amplitude alpha x. So if you square that, remember, if you square them, they must sum to unity. This is what the operation U does. It manipulates the amplitude. And you could say the whole artistry in universal quantum computing is to manipulate the amplitudes, to make the one result, the end of my computation, so the solution to my problem, to make that more likely when I measure the system than other results that I don't want to have. You will always see certain probabilities with even undesired results, even if you do everything right, because a quantum computer is a probabilistic system. But back to that. So such a permutation U, if we apply that to the unitarity, to the amplitudes, preserves the value, so the sum of the amplitudes. So it still takes unit vectors into unit vectors. So being norm preserving and linear, U is therefore unitary. And the transformations not, swap, and controlled not on classical bits are defined in this way on qubits as well. Available unitary transformations on quantum bits are much more general, you would say, than straightforward extensions of classical operations. Z, for example, that we briefly discussed before, phase shift, and H, the Hadamard transformation, for example, take classical basis states of a qubit. So classical basis states, remember what that is. So we don't have a probability amplitude, but we have definite states. These two, if we talk about single qubits, are classical, are definite states. So these operations, like a Hadamard transformation, take classical basis states of a qubit into another orthonormal basis. Like linear extensions to all qubit states are necessarily unitary. So remember, when you apply the Hadamard transformation to these two, you will receive two different results. So here you have 1 over the square root of 2 and a 0 plus 1. So and here you have 1 over the square root of 2 times 0 minus 1. So you have different relative phases, which means a different sign for one of the states, but that makes them orthogonal. And that means it gives you a new basis. So in that case, you would then talk about the Hadamard basis. And in designing quantum algorithms, the class of unitary transformations is almost always restricted to ones that can be built entirely out of products of one qubit unitary transformations at a time. So one qubit gates. Remember, or that act on a pair of qubits, like 2 qubit gates. So remember when I told you, even if that wasn't the case, because of current hardware constraints, you always want to have operations that minimize the number of qubits they act on. Because if you act on more qubits, the hardware will cause, so imperfections in the hardware will cause collapse of the system. So, and you will end the computation, so do an undesired measurement, so to say, before you are done with your computation. For a reversible classical computer, at least 1 3 C-bit gate or classical bit gate is needed in order to build up general logical operations, as we saw before. And a quantum extension of these 3-bit gates can be constructed out of a small number of 1 and 2 qubit gates. And unitarity, just to remember that unitarity is taken to be the hallmark of transformations nature allows us to perform on quantum state. What's really remarkable is their linearity, which is also one aspect of their unitarity. It's easy to imagine simple classical methods for a quantum bit, particularly if states are restricted to real linear combinations of the two computational basis states. So it's easy to invent classical models for NOT and Hadamard, 1-qubit gates that are, or that act linearly, say, on all the 1-qubit states of the model qubit. There's no classical model that can extend into controlled NOT on the 4 computational basis states of the 2 classical bits to an operation acting linearly on all the states of the 2 model qubits. Yeah. And it's interesting to note here that it's possible to fabricate unitary controlled NOT gates for a pair of qubits. What else? So I would say all classical computers work fundamentally in the same way. So of course there are different architectures, but basically they all work in the same way. And quantum systems are fundamentally different. So the size of the problem goes up exponentially in the size of the system, making them hard to simulate. And this is why in 1982, Feynman proposed quantum computers, right? So he asked that very famous question, or it isn't a really question. He said, nature is not, nature is quantum mechanically dammit, or is not classically dammit, something along these lines. So what he wanted to emphasize that if we want to make a simulation of nature, so simulate molecules exactly, for example, then we can only do that quantumly. And the question that sparked off quantum computing later was, so when people started looking into it, so why it's so difficult to simulate quantum systems with classical computers, does that in turn also mean that quantum computers are more powerful than classical computers? So in 82, so he didn't really directly propose quantum computers, but what he said sparked the whole field. So a quantum system should be able to efficiently simulate another quantum system. And efficiently in that case means that the resources used, which is time and size of the system, should scale at most polynomially in the size of the system to be simulated. So polynomially means as x, x squared, x cubed, so on. Okay, that's what polynomial scaling actually means. For a classical computer, as you know, so if we want to talk about a universal quantum computer, but again, let's start with a classical computer. So a classical computer, as you know, or as we talked about before, operates on a string of bits. So a quantum computer does that too, but we replaced this with a quantum state. So in terms of the representation, we talk of states instead of having a string value, having a bit value. So we are in states. And each digit, so it can be of length n, right? Can be whatever, however long. So this is how we write our quantum states. Each digit is a 2-level quantum system, a quantum bit. And quantum computers can be in superposition of these states. If we briefly remember how to write down a superposition, let me give you an example. So what's usually done is we talk about psi for a superposition. And what we have here is, so we have our n possible configurations. We start with x equals n, our bits, and we have our psi x next. So this is our basis vector that we have. Here we have the probability amplitude. So before we just denoted it with alpha. Here we have the possible states. So if we have 2 qubits, then this would be 1 qubit, then this would be 2 because we have 0 and 1 as state. And that's how you write that down. So you can represent that as a state vector too. The state vector that we just talked about before in terms of classical bits. For our probability amplitudes, in that case, it would mean you have our probability amplitudes here in this vector, and we execute our transformation on that vector. So this is also what we denote as the wave function. Operations on the state can be represented as matrices, as we talked about before already, and the allowed operations must be unitary. I want to give you one example, and one example, I mean, we talked about that a lot already, but still, I think iteration is improvement, so we'll talk about it once more. I want to talk about the NOT operation. So the NOT operation is given by that matrix, right? Then we have the application of NOT to the state 0 results in state 1 and vice versa. And a controlled NOT operation acts on 2 qubits. So it performs a NOT on the target bit, and it performs, so it does nothing, identity, it performs identity on the source bit. And so remember how you write that down in a matrix form. We did it a couple times, but let me give it to you for a 2 qubit system. So for a 2 qubit system, my controlled NOT operation would look like that. So you can definitely see here identity to the first qubit, not to the second one. And in terms of circuit notation, the NOT operation, controlled NOT operation, is just written down that way. And then you also remember we briefly talked about the Toffoli gate. Feel free to construct the Toffoli gate. I think we learned that in a couple lectures ago. Feel free to construct as a matrix, but in terms of a circuit notation, you would write it down that way. Okay, because you have a controlled NOT operation. The NOT AND gate, the NAND gate, is universal for classical circuits, and it acts as we learned before, but we can perform the same operation using a Toffoli gate. Okay, so let's just use or reuse that one here. If you have your input bits, let's say A, B, and you initialize that one as a 1 here, then the output would be AB and Q, and any classical algorithm can be converted to a quantum algorithm replacing the NAND gate, which remember is universal, with Toffoli's and keeping the extra qubit. And any function we could calculate on a classical computer, we can also calculate on a quantum computer with the addition of some extra garbage registers, right? So as we just learned before. Usually, so the method is always the same. So you add an ancillar or an additional bit and perform the program to give you the function f of x into your target register. You copy the output of the function into the extra ancillar bit. You give it, you invert the program. So, and then for ancillars that are not initially zeroed, you can just perform the XOR operation. So as we did it before, I erased that circuit already. Okay, that's always the same. So one part of the story is, of course, the superposition that makes it a little different. So if we're in a superposition of states, let's say we have n qubits, we can then evaluate an exponential number of different values of the function at once. But if we measure it, remember that, we will only find one value of the function. So if you look at it, it will collapse. And we'll talk about decoherence in that case. Now, we all know that modern classical computers are built from networks of logic gates, right? And quantum computing uses logic gates in a similar way. So networks of them are constructed to perform certain operations, and there are many more possible quantum gates than we just talked about. So in theory, there are infinitely many, but they must all be reversible due to their unitarity constraint. So we can represent them as a unitary matrix, like the NOT gate, and a couple other gates. This is the last thing I want to say about that. The most commonly used single qubit transformations, we learned about them already, are the identity transformation, or the NOT operation, or the Y operation, which is a or the set operation, which is the relative phase change of a superposition, and then Y, which is a combination of Z and X, a combination of the negation and the phase change operator. Okay, maybe we want to quickly write these down as a reminder. So we have our identity transformation, which you remember can be constructed for one qubit. We have our X operation, which, so again, you always remember which is the state you want to start. The state you want to start comes here on the right, but I will still write it down that way. 0, so makes 0 to 1, plus makes 1 to 0. Then you have the Y transformation, which is minus 1, 0, plus 0, 1. And you have Z operation. And a Z operation is given by that. So feel free to write that down in the matrix form too, but these are the most important single qubit transformations that we have. So again, IA is the identity transformation. This one is the NOT operation. The Z operation, or Z operator changes the relative phase. So you see the relative phase is only here of a superposition in a standard basis. And Y is a combination of Z and X. So it's a negation and a phase change. Okay, so the quantum analog of the NOT gate is easy to picture, as we saw, but other classical gates that we know are not so easy to transfer to the quantum world. All quantum gates, as remember, must be reversible, and classical gates such as AND or that we're so used to using are not reversible. So we'll not use these familiar gates as they require an effort to be useful and do not do at all what we require. So we'll introduce some new gates. And the first new gate that we already talked about is the controlled NOT gate. So I think we don't need to spend more time on the controlled NOT gate. You know how it works. We have the controlled NOT gate, the Toffoli gate, classically, that we saw, has 3 input bits and 3 output bits. And please, I want to encourage you, if you want to write down the matrix, so you know how to construct matrices out of the bracket notation. So please construct the matrix, and so even start with single qubit operations and construct the matrices out of these operations. We have the controlled swap gate or controlled exchange gate, which the classical analog is the Fredkin gate. And then we also have gates that have no classical counterparts. So, I mean, NOT, controlled NOT, swap, they all have classical counterparts. There are many other gates where there is no classical analog. So, for example, the Y gate has no classical analog. Z gate has no classical analog. The Hadamard gate is a gate that has no classical analog, so there is no superposition of states or superposition of bits in the classical world. We also have phase gates. So the phase gate denoted by S, is given by 1, 0, I, 0 here. Then we have the T gate. The T gate is 1, 0. with e to the power of I fourth. Then we have the rotation gate. So rotation gate looks exactly like that one, except that the exponent is changed to 2 pi I over 2 to the power of k. And they seem a bit arbitrary, but we have found them to be useful in quantum algorithms and diverse quantum algorithms. So no need to remember all of them right now. We'll talk about them later once we talk about the algorithms we're using them for. The next thing we want to talk about is quantum circuits in more detail, but that's reserved for the next lecture. Thank you.